there's a deep connection between chemical equilibrium and chemical thermodynamics. And in this video and the next, we're going to study and apply this connection by studying how the equilibrium constant K and the reaction quotient Q are related to changes in free energy, what we've called delta G in previous discussions of chemical thermodynamics. This connection between thermodynamics and equilibrium is at the heart of a lot of physical chemistry, and it really guides how we think about the favorability of chemical reactions in terms of favoring the reactant side or the product side in terms of energy changes and relative free energies, whether the change in free energy for a process is positive or negative, for example. And so this is a really important conceptual connection to make, because actually the way a lot of chemists think about chemical equilibrium is in terms of thermodynamics. We know which side of a chemical reaction is favored based on the sign of the free energy change and the relative free energies of the reactants and products. So in previous conversations about chemical thermodynamics, we've talked about spontaneity and how a lot of the, for example, second law of thermodynamics is based on how we understand what makes a process spontaneous or not, how we can express that in terms of entropy, and then the second and third laws of thermodynamics, which give us insight into what entropy tells us and what entropy means. And then we ended with the exposition of free energy, which is a concise way for us to understand whether a process is spontaneous or not. And free energy changes we represented as delta G, and noted that if delta G is negative for a process, that process will be thermodynamically spontaneous. It'll kind of just go. But there's a deep connection here between delta G and the equilibrium constant K and the reaction quotient Q. And we're going to make that connection in this series of videos. Now, before we do that, we need to turn the clock back on chemical equilibrium a little bit and review how we appreciate and understand chemical equilibrium. So let's start by imagining a general chemical reaction between little a molecules of A, a reactant, and little b molecules of B, another reactant, to make little c molecules of C and little d molecules of D. Now, a forward arrow is drawn here, but let's imagine that the reaction can be thought of as reversible. In other words, it may go in the forward direction or it may go in the reverse direction. And in any given chemical system in which this reaction is relevant, we might have non-zero amounts of A, B, C, and D. For that chemical system, under any conditions, be they equilibrium or not, we can write the reaction quotient, which is given right here. It's the ratio of the product concentrations raised to their respective stoichiometric coefficients to the reactant concentrations raised to their stoichiometric coefficients. And this, again, we refer to as Q, the reaction quotient. Now, in terms of free energy, we can think about the standard free energy change in terms of changes in the reaction quotient. And really, the standard reaction process is defined with reference to a specific starting value of Q. Specifically, the standard free energy change refers specifically to the process in which we start in initially the standard state for which Q equals 1. This is actually how we define the standard state, right? 1 mole per liter of all reactants and products, 1 atmosphere or 1 bar of all gases. And that's the initial state. And we start there and let the system evolve to a final state of chemical equilibrium. The second law of thermodynamics essentially tells us that if we just let a chemical system go, it's not going to go all the way to reactants or all the way to products. It's going to end somewhere in the middle. It may heavily favor products or heavily favor reactants, but in the final state, Q will have some value K that is not zero and is not infinite. And so the standard reaction process, again, we can think of as starting at Q equals 1, so the initial state is something like this, and going to the equilibrium state in which the reactant and product concentrations have their equilibrium values. So this is kind of a generic sort of ICE type table for this, where we're seeing how concentrations evolve over time during the standard process. And the free energy change for this process is, by definition, delta G naught, the standard free energy change. And it's important to note here that this is kind of a very contrived situation, right? We usually don't start with chemical systems having equal amounts of the reactants and products. The reason this is useful, though, is it's sort of the midpoint of the reaction, right? Where we have equal amounts of reactants and products, and we can observe which direction the system goes to get a sense of whether the reactants are favored or the products are favored. This is the utility of the standard process, really, and it relates to the sign of delta G naught, right? If delta G naught is negative, we'll proceed to the product side. Delta G naught is positive, we'll proceed to the reactant side spontaneously. More often than not, we're running reactions under non-standard conditions, meaning the concentrations and partial pressures of reactants and products are not equal to 1, and the initial reaction quotient, what we might call Q sub I, is not equal to 1. We're still interested here, though, in the free energy change in going from that initial state to the equilibrium state, because again, this is what nature does. This is essentially the second law of thermodynamics tells us that what nature will do if we start with a system having any value of the reaction quotient and just let it go, it will evolve spontaneously until Q equals K. And we might be able to harness some free energy from that process, going from Q initial to Q equals K. And that non-standard free energy change, starting from any initial value of Q, is what we just call delta G, without the little circle, right? Delta G without that little circle indicates a non-standard free energy change. But how much energy we can get, quote unquote, from a process, or how much we have to put in to get a process to go, depends on that value of the reaction quotient, right? One thing we can imagine, for example, is that if the reaction quotient is equal to 1, well, then the free energy change is equal to the standard free energy change, essentially by definition. But if the reaction quotient is not equal to 1, the free energy change, delta G, will adjust based on the value of the reaction quotient. And the way it adjusts is encapsulated in this equation. The free energy change starting from a non-standard initial Q is equal to the free energy change starting from the standard state plus a term related to the fact that Q is not equal to 1, the ideal gas constant, times the temperature in Kelvin times the natural log of Q. So a few remarks on this equation. Because delta G is usually in units of joules, the units of R we typically will use here are joules per mole per Kelvin, and that value is 8.314 joules per mole per Kelvin is the typical value of the gas constant that we'll use here. And naturally, with that being in per Kelvin units, we'll want to use Kelvin for this temperature, and that logarithm is the natural or E-based logarithm of Q. All right, so now we can calculate delta G given a standard delta G and a reaction quotient. And we should note here some trends in how delta G changes as Q changes. Notice that as Q gets bigger, as Q increases, we have an excess of products over the standard state in the chemical system. There are more products, at least in the sense of the numerator of the reaction quotient is larger than the denominator. There are more products than reactants, right? And this excess of products means that the reaction is a little bit less spontaneous, quote unquote, in the forward direction. Delta G becomes more positive, and it's actually worth pausing the video and verifying this math. That as Q gets larger, delta G will become more positive or less negative, and conceptually the way we think about this is the process gets less spontaneous, or we're able to harness less free energy from the system, given that we have more products than the standard state, right? On the other side of the coin, as Q decreases, well, in that case, we have more reactant than product, right? Since the denominator of the reaction quotient is larger than the numerator. The excess of reactants here causes delta G to become more negative and the process to become more spontaneous. And intuitively, this again should make sense. We've got more reactant there. And so from an entropic point of view, the system wants to make more products, right, to sort of increase disorder or energy dispersal within the chemical system. And so delta G becomes more negative. We're able to get more free energy out of the process, and it becomes more spontaneous in that sense. And less positive also applies here, right? So if we've got a process that is non-spontaneous because delta G is positive, adding more reactant can even push the process into spontaneous territory by pushing delta G from positive to negative, or can make it a little bit less non-spontaneous, we might say, right, by making the delta G value less positive. So intuitively here, again, it's important to make this connection between how changes in Q cause changes in the non-standard delta G. And these changes in Q can come about, for example, through Le Chatelier stresses. If we add product to a system, delta G becomes more positive. If we add reactant to a system, delta G becomes more negative. And actually, this connection between thermodynamics and equilibrium helps us understand Le Chatelier's principle on a really deep level, relating it back to delta G. In this practice problem, we're given a chemical system under certain conditions with partial pressures for the reactants and products, and we're given a temperature that's going to be important to use, and we're asked what is the free energy change for this process, again appreciating here that we're talking about the free energy change from this initial state that I've underlined in purple to the equilibrium state at the same temperature, which we don't know, but we actually don't need to know. Right? Using this equation on the previous slide, all we need to know is the standard change in free energy, which is also given, and the reaction quotient for the initial state. So the standard change in free energy, delta G naught, that's positive 33 kilojoules per mole. And the key equation to use here is that the free energy change starting from a non-standard state is equal to the standard free energy change plus the ideal gas constant times temperature. One thing to note about that R times T is this has units of energy per mole, and that is worth checking on your own if you haven't noticed this previously. We're going to multiply that by the natural log of the reaction quotient. And of course, before we can apply this equation, we need to write the reaction quotient, and this is a nice chemical equilibrium review here. We're going to write that reaction quotient as products over reactants using the balanced chemical equation that's given, right? So this is going to include the pressure of the N2 to the first power, since there is an implied 1 in front of that N2. We're going to have the partial pressure of H2 cubed, since there is a 3 in front of the H2. And then in the denominator of the reaction quotient, we're going to have the partial pressure of NH3 squared. So that's the reaction quotient in general. And for our specific system here, we're going to have the partial pressure of N2 is 0.870 atmospheres. I'll leave off units just to save myself a little space, and note that the reaction quotient doesn't have units anyway. We've got 0.250 atmospheres of hydrogen. We're going to cube that. And then in the denominator, we have a whopping 12.9 atmospheres of NH3, and that's going to be squared. Now we can calculate a value for that, and once we do that, we're going to plug that back in right here for the value of Q. And we're also going to use the given value of the temperature, which is 298 Kelvin, and the correct ideal gas constant value to use here. Well, this is going to need to connect to the units of delta G naught that are given. I'm going to go ahead and write this as 33,000 joules per mole. And the reason I'm doing that is because the R we're going to use is going to be in joules per mole per Kelvin. This will make the units work out nicely. And that R in joules per mole per Kelvin is the hopefully now familiar value of 8.314 joules per mole per Kelvin. And now we can essentially plug and chug. Before we do this, though, a couple of notes on this. So one thing we should notice about the value of Q, if we look back on the right-hand side of the slide again here, Q is going to be less than 1. Q is less than 1. This means relative to the standard state, we have an excess of reactants, right? Q is less than 1, meaning the denominator of the reaction quotient is larger than the numerator, so we have an excess of reactants. This will pull down the value of delta G relative to delta G naught. So we should expect a result here for the non-standard delta G that is less positive or even negative relative to the plus 33 kilojoules per mole. That's the standard free energy change here. And indeed, this is actually what we observe. So if you plug and chug, and it's worth pausing the video and plugging those numbers in, if you haven't done that already, we end up with 9,680 joules per mole for the non-standard free energy change. And that is equivalent, of course, to 9.68 kilojoules per mole. And so notice this is indeed less positive than the standard free energy change, which was 33 kilojoules per mole. And this is ultimately because the reaction quotient is less than 1. We're on the reactant side, quote unquote, relative to the standard state. The other thing I would point out here is the process is still non-spontaneous under these conditions. And by the process, again, we mean starting from this initial state underlined in purple and going to chemical equilibrium. What this tells us is that starting from this state, the reaction will actually not run in the forward direction. This reaction is going to run in the reverse direction spontaneously from this starting state. So just to sum up what we've seen in this video, we've made a connection between the free energy change for a reaction, the standard free energy change, and the reaction quotient of the initial state for the reaction. Noting that what we're mostly interested in when it comes to chemical thermodynamics is starting from some initial state with a reaction quotient Q and going to a final state that is chemical equilibrium. Essentially what happens if we just let nature take its course in accordance with the laws of thermodynamics. In the next video, we're going to deepen our understanding of the standard free energy change, delta G naught, making a connection between delta G naught and the equilibrium constant K.